The internet shutdowns are a whole other thing.
Okay.
Those are probably pretty bad for blockchains. Relatively recently, we had EU proposals to make like literally Euro transactions running on trusted hardware on phones, which had to be hacked in like days.
Sure, yeah.
And then people just like print themselves a lot of euros. And the ELVES protocol that does the sharding was basically Alistair, me, and Rob Habermeyer. If you can get a game company that actually has 10 million players a day, suddenly you need quite a lot.
I like this idea of like a cryptographic playground.
At the moment, what we should really focus on is shipping these host calls.
The launch team wishes you good luck and Godspeed.
Space Monkeys, blasting off with Jeff Burgess. He is a cryptography researcher at the Web3 Foundation, a gigabrain of the multi-chain. Here on the show with us today, Jeff. Welcome to Space Monkeys.
Okay.
You are working at the Web3 Foundation long time.
Yes.
When did you start there?
It wasn't very long after it was founded. Yeah.
We had Al on the show maybe about a year ago.
Okay.
I'm still like scooping up my brain, trying to figure out everything there. I mean, that was an amazing show. And today, while we speak, if I need you to slow down and help me understand a few things, I hope you don't mind.
Sure.
So what were you working on when you first came in? What were you hired to do?
I was at Real World Crypto in Zurich, and Harry Halpin was like, "Oh, I have to sell a Bitcoin because Amir Taki is sleeping, is crashing on my couch," and so we go to some bar, and we just end up talking with these people at this bar. And they're like, "Oh, what do you think about Whisper?" Or somehow they start talking to me about Whisper, and I'm like, "What's Whisper?"
Oh yeah.
And they explain it to me, and I'm like, "No, that doesn't. And that's not at all secure for these reasons." And I go on about that. And these people were Peter Saban and Rob Habermeyer and Ashley Tyson, and Rob then saw I was doing a bunch of stuff with Rust, so he told Peter to hire me. That's basically the story. Doing Mixnets is, it's a very worked over field. So there's a lot of stuff. It's important, but it's a very, very worked over field in terms of the research side of things. And there was just a lot of stuff, interesting stuff to do. So I ended up doing more sharding stuff.
So a few things I want to unpack there real quick. Whisper, we actually heard that recently on our programming here. Yeah. Can you give us a quick overview of what that was intended to do? That was kind of an earlier stage project.
Whisper is basically just a broadcast. I mean, the idea, it's one of these protocols that thinks you can get anonymity by broadcast. It's not, of course, scalable, and because it's not scalable, there will be serious weaknesses in the anonymity. You can still basically do all the timing attacks and everything else on the thing. So,
but it was meant to be a communications protocol.
Yeah.
Basically.
The truth is, network level anonymity is really hard.
Yeah.
There are a few designs. There's, of course, Tor. The problems at Tor is basically packet timing correlations. You can add latency to break the packet timing correlations. And there's basically a theorem that you need both.
Right, which is really intense and really slow.
But it adds a lot. It depends how much, but it adds a lot. And worse than being slow, if you send a lot of packets for a certain purpose, as soon as you get into something like transferring a lot of data and the amount of data is variable, it's just broken.
Okay.
So you can't do things like what Tor does. Doing what Tor does on a Mixnet doesn't obviously make any sense. I mean, there's other protocol designs like, Dining Cryptographers Network or whatever, which are better against that particular threat model, but because they scale very badly, they can only have very small anonymity sets. Anyway, so there's a whole space here. It's a very worked over space. People have tried many things.
This was the next thing I wanted to get to. Could you give us a quick overview of what a Mixnet is, and maybe in reference to language that we understand?
It looks like Tor. You forward some packets, but in the Mixnet, each packet is being forwarded over a random route through the network.
Okay.
A different random route. And that would de-anonymize you very quickly if you're sending a lot of data, because soon you'll hit a route where all the nodes are bad.
Yeah, okay.
When the mixing itself is actually the adding of latency. It's that a packet comes in, a packet waits, and it is mixed with all the other packets that are waiting at the same time.
Sure, okay.
So Tor is like a Mixnet minus the mixing.
It's kind of like a token tumbler, but for data packets instead of tokens.
Yes, yeah. Well, that's where the idea for the token tumblers came from, is from this kind of thing.
Very cool.
And the real problem with these things is actually somewhat similar to a problem we have in the blockchain space, which is that to make a Mixnet work, you need applications that are very resilient to like data latency and whatever. And we know how to do this. It's Git, like DVCSs or something that are using context-free replicated data types are preferable to that kind of thing. But this means that you then need every application that you're going to use over this thing needs to somehow interact with its own storage in that way so that you can like share the messages. I mean, something like HackMD does this to some extent under the hood, but there's this layer between the application and the underlying transport. Everybody who gets interested in this stuff wants to go and work on the transport, but there's another layer there that is actually the important thing that is kind of the gateway to making Mixnets work. And it's also the gateway to making applications work when you've got like collapsing internet infrastructure or people or governments shutting down the internet or whatever. So there's, which maybe is even more important. There's a certain parallel to the blockchain world in that, people want to go work on the L1, they want to go work on the thing, and they especially want to go work on the thing that's going to give them a nice token. People build something there, but they're not really churning on it to get something that is really going to get a really nice experience there.
To have a truly resilient state machine.
Well, okay, so the internet shutdowns are a whole other thing.
Okay.
Those are probably pretty bad for blockchains.
Yeah.
Pretty much for all the blockchains. I mean, they choose to deal with it in different ways. Bitcoin chooses to ignore the problem.
Okay.
So that will just, if you have an internet shutdown, a major internet shutdown, Bitcoin will just be rampantly double spent. So it's basically not something you can use in that situation.
Yeah.
All of the proof of stake networks, Ethereum, Polkadot, whatever, those at least you can tell if you can use it or not.
Oh, okay.
Which is a major advantage.
So at least won't get wrecked.
Yeah, you're not going to get double spent against rampantly in that situation. You can know whether you're getting finality or not. Whereas with Bitcoin, you may not even know. People who are doing these government cryptocurrency ideas.
CBDCs.
Yes, a bunch of the people who are doing that, not all of them, but a bunch of people who are doing that actually want to use trusted hardware for exactly this reason. And that would be a disaster. And like periodically somebody who's talking about trusted hardware for this stuff.
Yeah.
Relatively recently, we had EU proposals to make like literally Euro transactions running on trusted hardware on phones, which had to be hacked in like days.
Sure. Yeah.
And then people just like print themselves a lot of euros and do whatever. So
when you say trusted hardware, are you talking about like trusted execution environments?
Yeah. So I mean, like literally, everybody has a device.
Oh, they get a separate device.
Everybody has a device. Well, the EU people were thinking it would be your own fucking phone.
Yeah, I got you. Yeah.
But no, you have a device and you can do a transaction with somebody and it's purely offline.
Yeah.
So it's perfectly scalable, perfectly anonymous. It's everything you want, except that it requires the trusted hardware actually exist. And, Intel SGX is broken every 6 months. And like there was a super bad break of SGX this year.
Right.
So Intel's putting SGX in fewer and fewer chips because, they're trying to restrict the customer base that uses it to the ones that really want it. Anyway.
Just to catch people up there. So we're talking about trusted execution environments, which is a piece of...
It means a hardware where the hardware runs some piece of identified code and signs that it ran this thing, and you can actually trust that.
Yeah, it's isolated from the rest of the...
Yeah, but the problem with trusted execution environments is the threat model is really terrible. You're dealing against a person who has physical access to the piece of hardware, can manipulate the power, can cut into it and manipulate bits in it and everything else. So I actually do kind of think this is physically possible to build a trusted execution environment, like a good one.
Okay.
But I think the research project to build that would be like a few decades, and like tens of billions.
And it might not work in the end anyway.
It might not work, but like the stuff that people are shipping now, I mean, a ledger is designed to keep you from breaking in, but it is not designed to really run while not being broken into.
Gotcha.
It is so the kind of thing we're talking about here is something a whole nother level of difficulty.
At the beginning of our conversation, you said you were at a conference which was called
Real World Crypto,
and you said in order to speak there, you had to be talking about cryptography.
I mean, that's an exaggeration. They've had Zcash speak there basically.
Okay,
and almost nobody else.
But by and large, this cryptography that's being discussed needs to be affecting millions or billions of people. What are some examples of cryptography that does have a large scale
anything
impact?
that Google or Apple does.
Okay.
The usual people who are very prevalent at that are people involved in the IRTF stuff, like the standards things, people involved in TLS. He's usually like a session or two on TLS.
Okay.
So it's an extremely good conference because it's very close to like what is actually going to be really happening and all of the real world concerns. Whereas when you go to something like Philip Rogaway has this wonderful paper called the Moral Character of Cryptographic Work, and he gives one of his statements in this is that he saw some report on like some NSA agents who went to Eurocrypt and basically said like, nothing here is a threat. Because it was all very theoretical.
This was your core area of interest, I guess, and then you met Rob and crew at the bar, and then you transitioned to blockchain, right?
Yeah, well, they hired me to do Mixnets, but deploying a good Mixnet is as hard as doing what we've done, and it requires a lot of work that is more on the application side, like I was talking about.
Yeah.
And so it was just more fun to worry about the scaling because it's more. People have different temperaments, and this fits,
What are you actually working on at the Web3 Foundation
Right, yeah,
today?
let's talk about that kind of thing.
Yeah.
A lot of what I do is just kind of keeping track of what people are doing on Parity's side and how research can help it.
Okay.
A lot of what I have done in the past is sort of protocol design, so the ELVES protocol that does the sharding was basically Alistair, me, and Rab Habermeyer. Alistair had the initial idea that the availability should be a one-dimensional erasure code. I showed in the paper by Vitalik and Mustafa about the two-dimensional erasure codes, and he the next day he was like, no, we should use a one-dimensional erasure code because it meshes with the two-thirds honest. And since then, everything we've been doing has been trying to target this two-thirds honest assumption, so we have the same security assumptions everywhere. So what I did, he and I came up with this idea of using VRFs to assign checkers, and then eventually I went and tried and made it more formal and deal with all the corner cases and shit and make it actually make sense.
Okay.
Rob and I worked a lot on the design and implemented it. And then eventually, Alfonso and Alistair and Chendan were able to produce a security proof for it. Because that means that we have this scaling, which is very efficient. It was designed from a practical perspective with an eye on having security arguments eventually. And we succeeded. We got lucky. The security arguments actually worked.
We're there, yeah.
A way you can measure sort of blockchains is you can ask sort of what's the total CPU around like producing and dealing with a block, including the verifying.
What's the frequency of checking?
Just talking about checking every block. So making a block, which is 10 megs, 2 seconds of execution. All of that needs to be done on around 45 machines, including the parachain ones, including the collators.
Yeah.
So certainly something like Cosmos or, Definity, their best chains are about that big. But the difference is that we're doing it all within the same threat model. So all of these chains can trust each other and talk to each other.
That's the crazy thing, yeah.
And so that was one thing that I had a huge role in. Another one was Sassafras. So,
Sassafras kind of never really
well, it's
really
going to be part
in.
of Jam. It's one of these.
Now it's called Saffroll.
Saffroll is still Sassafras.
Okay,
the paper,
let it be known.
The paper doesn't talk about these other things.
Okay.
So what Saffroll, the only difference is it removes two things that I shoved into Sassafras because they made sense on parachains.
Yeah.
In Sassafras, as it was originally implemented, there were two public keys per block. One of them was when the block was created, the secret key for this public key would be revealed. And so the idea would be you could encrypt upcoming blocks. This is not as good as, say, using identity-based encryption with DRAND or something, or having a DKG amongst the validators that then supports doing this. Those are better. So that removing it is fine because we'll probably do a DKG amongst the validators eventually anyway. But the other key was a key that when you created the block, you signed it and then destroyed the secret key. And but the other use of this was that you could use this as a Tor hidden service URL or some identity in a Mixnet or something. And so you could talk to the collator before they make their block, which means you don't have a mempool, which saves you more than half your CPU on the collators.
Okay.
And lets you do all kinds of weird MEV defenses and stuff like that. But that's not particularly relevant for the relay chain. So I don't care that that's removed from the relay chain. Polkadot is partly Ouroboros prowess, and then to have 6-second blocks, it adds in this round robin thing. The disadvantage of that is you have, in expectation, you have 2 or more blocks in most slots, or in many slots.
Yeah.
So you get a fork every couple relay chain blocks. Now that is quite bad for performance. That really hurts our performance a lot. It is quite good for building robust code. It has made Polkadot much more robust. And unless Jam is very careful, they're going to lose that. But it needs to be eliminated eventually. So Sassafras removing it is a good thing.
Gotcha.
So what Sassafras does is it's just a block production algorithm. It's basically block production by Cards Against Humanity. Like VRF protocols can often be thought of as card games. You have a VRF, there's some randomness, and your VRF defines the cards in your hand. And then you can play one by producing a signature. And so at this particular height, here's your card. If it's a good card, you get to play it. If not, you don't. What Sassafras, the problem with that is there may be nobody with a card at a certain height or too many. What Sassafras does is everybody makes up some cards ahead of time. And instead of signing them with a VRF, they sign them with a ring VRF, with an anonymized VRF. And it proves you're a validator or a collator, but not which one. And then you play it through an anonymity layer, which is like playing it face down, like you do in Cards Against Humanity. And then the chain sees them face up at the other end of the anonymity layer, and sorts them
without knowing who put it down.
Yeah, without knowing who puts it down, and the chain sorts them, and that becomes your block production order.
That's cool.
And so it's literally just, we play all these cards, we sort them by how funny they are, and that's the order in which you play. You get to make blocks.
Very cool.
By how small they are instead of how funny, but
Is that just like a great outcome, or is that something that's actually being worked on?
I mean, it's been implemented. It was implemented a while ago for Substrate. We never deployed it. That code in Substrate was ported over to Jam, and we're not going to deploy it before Jam, I think, because it isn't a crushing need. It just makes our performance worse, and we have bigger things to fry, bigger fish to fry.
Performance really isn't our problem, actually, as we showed yesterday.
But it is. I mean, we have the whole parachain teams working on improving it. We do need to be working on it because whenever we can get some successful thing, they can start sucking up a lot of performance very quickly.
That's true. Yeah, we got to be ready.
Somebody can if you can get a game company that actually has, 1 million players a day, or 10 million players a day, suddenly you need quite a lot. Coming. And when I say players, each one doing a lot of transactions. So the same construction, these anonymized VRFs, we can also use as an identity system. So we actually got the idea there from these proof of personhood parties by Brian Ford. I mean, we got the idea because we knew we needed, because people were talking about SSLEs.
Which are what?
Secret single leader elections. And so we were talking about it, and at some point, Alan and I figured out this idea, and at some point I wrote down a list of possible things we might do as an SSLE, and including the shuffle stuff Ethereum wants to do with Whisk. And I didn't know all the optimizations that they have, but it was still obvious that the shuffle's less efficient just from back of the envelope calculations. We've very extensively optimized the ring VRF. So, and we have another set of optimizations for it, which are good for identity. I mean, basically, what the ring VRF is it lets your secret key defines a function, something like a hash function. The evaluation of this function, once you've anonymized the signer, the evaluation itself becomes their identity in the context that's the input to the function.
So
an Ethereum has something similar. They call it semaphore, but it's not very efficient.
What are some of the lowest hanging fruit you can describe to us, and how that would
one appear? Really low hanging fruit, which is we need to merge these host calls that give us elliptic curve operations. And there's a few things to do there. We have a list of curves that are not in the stuff that's already implemented in Substrate, but that the community has asked for. And so those have to be added.
Like what?
We support the Ethereum SecP signature.
What's SecP?
the SEC P256K1, the Bitcoin curve. We support the Ethereum form of that signature, which uses this EC recover stuff, which is not a good idea. But anyway,
Okay.
all of the other stuff that people are doing on Bitcoin with that curve, first of all, the underlying signature is not the EC recover thing. It's something else. It's a more standard ECDSA signature. And then now they're doing the Schnorr signatures with it. To let people like do that stuff on Polkadot, we should just, instead of supporting adding a host call for each possible thing that people want to do with that curve, we'll just provide like 2 host calls with which you can build any protocol call using that curve.
What results would that have?
You can do anything you want in WASM now.
Yeah.
I mean, you can take the Rust, compile it to WASM, and it will run. If it's cryptographic code, it will run probably about 10 times slower.
Oh, okay.
Because cryptographic code is very highly optimized. And PolkaVM, I'm not sure how much faster PolkaVM is than WASM, but it won't necessarily improve on this very much. At the moment, what we should really focus on is shipping these host calls. They're the guts of like a Rust elliptic curve library. So what you can do is you can take something you write, a piece of code you have that uses ArcWorks.
What
ArcWorks is a framework for building snarks and things.
Okay.
So like ArcWorks has these elliptic curve abstractions. Most of the fancy snark libraries have some kind of elliptic curve abstractions. So what you can do, once we ship these host calls, you can take ArcWorks or some other fancy crypto using elliptic curves thing.
Okay.
And just, these frameworks are polymorphic over the curve.
That's cool.
You can basically just swap the curve implementation from the native one to the substrate one that will then just use these host calls. So your Rust code will just work. And that means that we'll have an incredibly friendly user experience for just deploying fancy cryptography on substrate.
You know, word on the street is that maybe Kusama will become this hotbed for
Sean
zero knowledge stuff.
Sean is talking about this basically because he knows that all we have to do is merge these things that I had people implement a year or two ago now.
Yeah. What do you think about that? I mean, that'd be pretty cool if we had like this, like, industry Polkadot layer, and then we had like this dark Kusama layer.
The answer is we should have shipped this a while ago. We just didn't because we weren't getting enough. Because there were 1 or 2 things I wanted audited in it.
Oh, okay.
And I wasn't pushing it hard enough.
Okay.
At this point, I would say, especially for Kusama, we can just ship what we have and then
see what happens.
And maybe that'll be the impetus it takes to finally get the right kind of auditing of the host calls. I don't know.
Okay, cool. I like this idea of like a cryptographic playground.
So that's part of why we designed these host calls this way is to make the playground side more efficient. Yeah.
That's cool.
So one thing, just some comments on the performance thing maybe from yesterday.
Talking about the spamming.
Yeah, the spamming. There's a lot of stuff that was even already merged, but not on validators that would improve it, including light P2P.
Right. And if I have this correct, this is like, right now we have like this gossiping overhead.
Yeah.
And this is like
we'll always have gossiping overhead. It's more just the internal overhead of libp2p is fairly high.
Okay.
It's actually internal. It's not really about the network at all.
Oh, sorry.
The network messages should be the same.
Oh, okay.
I would like to change how our gossip topology works because I'm pretty sure we can save quite a bit if we change that somewhat. But that is not properly designed yet. I'm pretty sure I have the ballpark of a design that will be much more efficient.
Okay.
But currently we use this 2-dimensional grid and we have separate from that a random graph. But the problem is they're completely separate and I don't know of any good reason for them to be separate. What would probably make more sense is add a little more latency, use a 3-dimensional grid and have it unified with random jumps. Anyway, so there's stuff there that we can do to improve the gossip that will save a ton of CPU. There's a bunch of things the Parachain team have already done and are implemented, but we're not. It takes a while to get all this stuff out to the validators.
Yeah, sure.
And this is not on-chain stuff. You can't do it with a host with a runtime upgrade. You've got to force the validators to upgrade the host.
Yeah, it takes a while to propagate among.
Yeah, so there's a whole bunch of optimizations there. We're not using batch verification, which would save us 40%. We can ask the validators to increase the specs. We're only asking for like 4 cores right now, so we can maybe on Kusama they're not even doing that, some of them, but you could easily ask for 16 core machines, and we could really go more than that if we start, And maybe that's even a good thing going more than that, because maybe it forces people off of, some of the, Amazon and whatever.
Yeah. Yeah,
There's, if we do a validator GKG, that's come up a few times. At some point we will. We actually know how to cut the number of approval checkers in half if we do that, which just doubles the number of cores.
Wow, really?
So, Nompt, this thing by Rob Habermeyer, Nompt.
Yeah.
Nompt, that's a 4x reduction in the block size.
Mm-hmm.
Probably it won't give us a 4x improvement in those numbers, but if you imagine we switch to batch verification and Nompt, then you certainly get a doubling. We can do some other shifts there so Nompt's important. In the end, it will enable a 4x improvement on those numbers.
So
once we do some other shit.
128,000 TPS we did in production, but I mean, even in the short term with more cores, this could be 1 million on Kusama with minimal improvements.
Not with minimal. There's a bunch of changes. So these are not
even just adding
changes,
more cores.
all of them.
Yeah.
So there's a lot of more basic things that the Parachain team works on that are very important, like finding bottlenecks and other things like this. Every Jam project is going to have a year of work on that.
Okay. Yeah. Good thing the prize is so big.
Yeah. In terms of like the optimization of all of this stuff, there's just this weird asynchronous protocol thing. There's a lot of different optimizations you can do. That will take a while. We're still doing it. So they had 60 cores to do this on. They were only willing to do it on 23 because they were afraid of crashing the thing using all 60.
Sure.
So Gavin came up with similar sort of imaginary numbers that I did. I mean, he said something like 6 seconds of execution on something like 300 something cores.
Oh, yeah.
What I was always saying is we reach parity, which means we have 2 seconds of execution on 1,000 cores on 1,000 validators. These numbers are coming out of theoretically looking at what the different things are.
Yeah.
Maybe we don't get there. Maybe we never reach parity. But with better hardware, with all of these other optimizations, it looks possible.
Crazy.
And then we could do multiple relay chains if we need to, but that's a whole other thing.
Yeah, no, I know. What was it? The Galactic Jam Grid or something like that?
Yes. So actually any distributed protocol can do this, including other blockchains. Mm-hmm. So what ELVES does, what the approval checking system does, is it makes the adversary commit to their block before we decide who's going to check it.
Okay.
And that's why it can get down to like 30 checkers.
Ah.
Well, what multiple relay chains has to do is assign the validators to the relay chains in advance. And that means then you have to worry about a concentration of adversarial nodes on a particular one. So the fundamental theoretical tool here is what's called a concentration inequality. It lets you talk about the probability of something being far from the expectation. You need some good randomness, like a validator, DKG, and threshold VRF. You use that to assign enough validators to each relay chain, like 1,000 basically.
Yeah.
Put around 1,000 on each relay chain.
Yeah.
And then you have to assume something more than 2/3 honest. You have to assume something like 80% honest, which really means you should be doing more community work to make sure the validators aren't colluding and other stuff. Anyway, you need to make some stronger honesty assumption, and then the concentration inequality will prove that with very high odds, each of the relay chains is 2/3 honest.
Is it possible to have multiple relay chains under the same security assumption?
Yeah, that's precisely.
This is what you're talking about.
Yes. Then there's no grid. They just use beefy bridges between them.
Yeah, got you.
And the hardest parts of this is probably the validator DKG, because those things are finicky. But there's a bunch more design work to be done there.
Okay.
But it's that will certainly not happen before Jam happens, because we don't have enough usage for one relay chain right now.
Yeah, fair
I would
enough.
say we really need to sort of be feeling like we're filling up one before we do this.
We can't get ahead of ourselves.
And also
again.
because there are a lot of plans. There are lots of ways to do the scaling more. This is not our problem. Shipping EVM so that all the EVM people want to build on Polkadot is one thing. Shipping something so that you can really build real data partitions, Web3 applications is a whole other problem. And we need to be doing that also.
Well, we are, right? We're working on both.
Not enough.
Okay, well, maybe this will help people get more inspired to do so.
Yeah, I mean, somebody should probably take a look at like what. I mean, one very simple question is, of the Web 2 frameworks, like the big framework things that people use, which ones are like really great for having your databases on different machines?
Yeah.
And what have they done? These are. Maybe you get some ideas thinking about that kind of thing. I don't know.
That's lots of material, and giving us lots to think about and chew on. Thanks for all your research work and for sharing with us today. And I don't know, let's maybe check in a year or so, and we can go far out again.
Okay.
So thanks a lot, buddy.
Okay.